again. So the topic that we are going to study today is one of the sorting methods known as heap sort. Okay. So when we're going to study heap sort, the first thing that you need to know is what is a heap. Now this concept of heap comes under trees. Okay. So in today's lecture, we'll not be learning heap sort directly. But first we need to know what is a heap. The entire lecture may go in understanding what is a heap. And then once we understand what is a heap, how a heap is to be constructed, how elements are to be added to a heap, how elements are to be deleted from a heap. Once we understand all this, then we can go and understand the concept of heap sort. So most likely heap sort topic will be done tomorrow's lecture, and today we'll be studying what is a heap. So let's start with it. So basically this is your definition of a heap. Okay, please note it down in your notebooks. So your heap is having two properties. One is a structure property. So basically your structure property means that all the levels in a binary tree have maximum number of nodes except the last level. In the last level, all the nodes occur from the left side. Okay, the meaning of that is, suppose we are having a tree, okay, a binary tree. So all the levels that are present in the tree will have maximum number of nodes. So this is level 0, level 1 and so on. So on level 1 we have studied the property of the trees where maximum number of nodes that can be present on this level is 2. Similarly on the next level we can have maximum number of nodes. This could have had 2 children, left child, right child. This node could have had 2 children, left child, right child. So this is on this level. So what it means, all the levels will have maximum number of nodes. So now you have seen, till now I have drawn 3 levels and all these levels are having maximum number of nodes. So except possibly the last level. So in the last level, all the nodes, if they occur, they will occur to the left. The meaning of that is, suppose I am having nodes like this on the last level. Suppose this is my last level. Then the nodes, if they occur on this level, the last level, they will occur on the left. Okay, I will not have a case where one node will occur here. Okay, this will not be happening in a heap. So if you are having a heap, that means a heap will be present like this. So basically we had studied in binary trees or in trees when we are studying, we had studied one definition for this type of a tree. What is this type of a tree? Wherein all the levels are full, all the levels are having maximum number of nodes except the last level. And at the last level, all the nodes will occur from the left. What type of a tree is this? We have studied this definition before. What is the definition of that tree? Yes, correct. It is a complete binary tree. Okay. I had asked you to read this definition. So I hope you have read this definition also. So this is a complete binary tree. Okay. So one property of a heap is it will always be a complete binary tree. Okay. So something always will be something like this. This also is an example of a complete binary tree. So when you do the numbering, we have seen how you do array representation of a binary tree. So you know, while doing the numbering for array representation, you start from 1, this will be 2, this will be 3, this will be 4, and this will be 5. So basically the numbering of the nodes will be continuous. So this will be a complete binary tree. So that is your first property or the structure property. Okay. Now, second, there's one more property of your heap, that is the heap order property. So in the heap order property, the key value in any node n is greater than or equal to the key value in both its children. Meaning is, the parent value, the value of the parent will be greater than the value of its child nodes. So for example, if this value here is say 50, okay, the value of this node, the root node is 50, the value of its children will be less than the value of its parent. So here the value could have been say 30, here say the value could have been 20. Okay. Similarly here, and this order is throughout the tree. So here you are having the left child of 30. So this value will be less than 30. So say it could be 29. Say this value could have been 10. Okay. So throughout the tree, the value of the parent. Now this is the parent. This is the left child. This is the right child. The value of the parent node is greater than the or equal than the values in its children. Okay, and this property is satisfied throughout the entire heap. So both these properties, when they are satisfied, that time we call it as a heap. Is it clear? Have you understood? Any doubts about this definition? Please write down this definition and keep. You need to refer to this definition throughout this, at least both these lectures that we are going to do, today's lecture and tomorrow's lecture. You need to remember this definition. Please note down this definition. Now, before I move over to the next slide, anyone has not understood any of these properties, these two properties that we have just referred to? First one is the structure, second one is the heap order property. Is it okay with everyone? Okay, let's continue then. Now, one thing to be noted is, okay, we could have had two types of heaps. Okay, we could have had two types of heaps. So one type of heap is a max heap, which we have defined on this previous slide. Okay, we have defined the definition. This definition that we are given here is of a max heap. In a max heap, the value of its parent is greater than the value of its children. Okay, value of a parent node is greater than the value of its left child and its right child, and that property is throughout the entire tree. So you can see here in figure 6.127, all these are examples of max heaps. So you can see here 56 greater than 43, 55, which are its children. Similarly, 43 greater than 9 and 5. Okay. And throughout the tree, this property will hold. That is this second property, heap order property. The first property also holds, wherein it is a complete binary tree. So if you do the numbering will be continuous. Okay. The second type of heap that we have is a min heap. So if you change this definition that we had, the second property that we had, instead of saying greater, we said the parent value will be smaller than its left child and right child, then we get a min heap. So in the min heap, the value of the parent is less than or equal to the value of its child. So here you can see the root node value 70 is less than its children value 75 and 96. Similarly, 75, this parent value is less than its children 80 and 95. Similarly, this parent value 96 is less than 98. So such a type of heap is called as a min heap. So throughout, so you can see here, this all are the examples of min heaps. So to get the definition of a min heap, you just need to change in the second property, change the word from greater to smaller, and you get the definition of a min heap. So max heap is also called as a descending heap, and a min heap is also known as a ascending heap. Now, heaps are nothing but trees, okay, binary trees. They are binary trees, but they are not binary search tree. They are binary trees, but they are not binary search trees. So can someone or can everyone, can you, what is the difference between a binary tree and a binary search tree? What is the difference between a binary tree and a binary search tree? Yes, Siddesh. Yes. It is not compulsory. It could be any value. What is important is, Siddesh, in a min heap, value of parent is less than value of its children. It does not matter whether left child is greater or right child is greater. Okay? It does not matter. In heaps, it does not matter. Only if you are doing a max heap, the value of parent should be greater than the children. If you are doing min heap, value of parent should be less than the children. Only that is the property to be looked at. Does not matter whether left child is greater or right child is greater. Yes, Yash has mentioned here, left child is less than the parent and right child is greater than the parent. That is a binary search tree. So what is the difference between binary search tree and binary tree? Huh? Ashish? Can you tell me, Ashish, what is the difference between a binary tree and a binary search tree? You are not reading, it looks like. Okay, students, you need to revise. We started with unit 4 and you have stopped revising. You need to revise. Okay, you need to find out and you let me know in tomorrow's lecture. All of you, you need to revise. Okay, so let's continue. So till here, has everyone understood? In the first slide, we saw what was the properties of a heap. We said that first property is it will be a complete binary tree, that is your structure property. And second property we said heap order property. That is, if it is a max heap, the value of the parent is greater than the value of its children, or it could be equal also. And if it is a mean heap, then value of the parent is less than the value of the, or equal to the value of his children. Okay, is this clear? So now in your textbook, throughout they always use max heaps. Okay, so in the rest of the examples that we will be studying today and tomorrow, will be only referring to max heaps. So remember, mean heaps also are occurring, so don't forget about mean heaps. So you can just read this slide, why we need to use a heap. Okay, you can just read this second para here, why heaps are required. And how are heaps represented mostly? Just read the second para and the third para. So as you are reading the second para, can just, it's common sense actually. Why do we require heap for this? Where we need to determine the largest or smallest value quickly. Why heap can be used for that? If you have understood the previous slide, then the answer is very simple. So like we have discussed, heap is a complete binary tree, okay, and it is implemented using arrays, okay. Because it is easier to move up and down the tree using arrays. In linked list, like you know, we have to maintain pointers to move up and down the tree. Whereas in arrays, we just use this formula where the left child will be present at 2. If the parent is at index I, then the left child is present at 2i and the right child is present at 2i plus 1. Okay, we had discussed this during the when we were studying trees. So that's why we prefer to implement heaps using arrays, because we can apply this formula. So going across the moving up and down the array or accessing the children of the nodes becomes very easy using arrays. Okay, so can coming back to this question, can you all write in the chat why we are using heap to find why we need to use heaps if the largest or smallest value has to be determined quickly? Correct. So all these students here, Riya, Vibhuti, Cheryl, Suraya, have answered that. Yeah, that's the correct answer. If you have observed this previous slide, okay, and according to the definition, the second property, heap order property, the parent value will be greater than its children. So if this value, the root node value is greater than its children, that means this will be the largest value. Okay, as you can see here, in a max heap, the value of the root node is the largest value in the entire tree. Okay, you can look at all these examples that are there. Max heaps, 56 is the largest value here, 90 is the largest value in this third one. Okay. Similarly, in the min heap, the smallest value is present at the root node. Okay. So that's why we can use heaps to find the largest or smallest values very quickly, as long as this property is satisfied. Okay, both these properties. That first property is the structure property, and second property is the heap order property. So heap order property for a max heap or heap order property for a min heap. So that's why we say heaps are mostly used in problems where the largest or smallest value has to be determined quickly. Okay, it's also mentioned here picking up the first element. So why we are picking up the first element? Because the largest value in case of max heap is present at the root node, and smallest value in case of min heap is also present as the first element. Okay, when you are representing these trees using arrays. Clear? So this is the way you would have represented a heap. We have already seen this while doing trees, so I won't go into details. So you can see here, when you are doing a program, you can maintain a variable to maintain the size of the heap. So the maximum size of the heap here would have been 12. Okay. As you do the numbering, you know the numbering is continuous. Because the numbering is continuous because it is a complete binary tree. Okay. In a complete binary tree, we said the definition is that all levels will have maximum number of nodes except the last level, and last level will have nodes from the left. So because of that, the numbering is continuous, and it would have been stored in an array something like this. And then we would have applied this formula. If you wanted any left child or right child, we would have applied this formula 2i or 2i plus 1 to find out the left child or right child of a node at index I. So for example, if I want the left child of 45, then this value 6 is suppose I, the value of 45 is present at 2i, that is 2 into 6 present at 12. And if I wanted right child of 45, then it would have been 2i plus 1, which would have been 13. But 13 value is violating the size of the heap, which is 12. Therefore, we say that 45 is not having a right child. Okay. That is when you are doing a programming, you can make use of all these properties of trees to do the programming. Okay. So this slide is just to represent your heap using arrays. So this is the way it would have been done. So shall I proceed? Is it okay with everyone? These things are already previously done, so I'm going a bit fast. Okay. Coming now to one important thing in your insertion property. So now suppose we want to insert elements into a heap. Suppose you're already having a heap. Just say you're already having a heap. Okay. And you want to insert a element into that. So say we want to insert this key 70. So this is your original heap having size 10. Okay. And as I told you, we are referring to max heaps now throughout the book. Okay. So this is a max heap with size 10. And first property is satisfied, wherein it is a complete binary tree. And second property is it satisfies the heap order property. So both these properties are satisfied here. You can check out. Okay. Then now we want to insert 70 here. So when we are inserting 70, we will insert 70 as a leaf node here. We insert 70 as a leaf node here. Why insert 70 as a leaf node here? Because we want to maintain the first property, that is the structure property. If I would insert it somewhere here, say, then the structure property would not be satisfied. Okay, I would not have this thing as a complete binary tree. And if it's not a complete binary tree, then it would no longer satisfy the structure property, and it will no longer be a heap. That's why what we do, we insert a new element as a leaf node such that this property is satisfied, that it remains a complete binary tree. So if the size of the current heap was 10, we insert the new element in the 11th position, where a new leaf node would be present at the 11th position, like it can be seen here. So I insert this 70 at the 11th position, so that my property, the first property of the heap, is maintained. It remains a complete binary tree. Okay. Is it okay? Why we are doing this? So this is the first step. You insert 70 here. Now after inserting 70, so you have satisfied your first property, that it has remained as a complete binary tree. Okay, you do the numbering and you check. The numbering has to be continuous. So you can check here, it is continuous. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this first property is satisfied. So you are happy with it. So go and check for the second property. The second property, your heap order property. That is your heap order property. Okay, check for the order. Check here. Is this value greater than its children? Yes, it is greater than the value of its children. Come here. Is this value greater than its children? Yes. Check this. Value greater than its children? Yes. Come here. Value greater than its children? Yes. Check here. Value greater than its children? No. There is a problem here. Okay. This property is no longer satisfied. That is, max heap property is not satisfied. Value of parent is not greater than the value of his children. So we need to change this. This is not satisfied. We need to do something about this. Is it clear till now what I have told you? Clear, everyone? So first of all, you have to do something about this part where it is not proper. Okay, the second property is violated. Heap order property is violated. So to restore the heap order property, we can do something known as a restore up function. Okay, that is there in your textbook. We need not refer to that. We can just say to that we need to restore the heap order property. So to restore the heap order property, this is the way it is done. It's quite simple. The problem is here. The problem is here. Okay, this value and this value, there is a problem. So we exchange these values. Exchange 46 and 70. So when you exchange, it will look something like this. 46 will come down and 70 will come here. Okay. You compare then this value with its new parent. So this is the new parent. You compare 70 with 59. Again, you find that there is a problem now. Okay. When you compare with the new parent, you see that this parent value 59 is less than 70. So what you will do? Exchange again. So 59 will come down, 70 will go up. So when you exchange again, it will look like this. 59 comes down and 70 comes here. Now you compare this value 70 with its new parent. So this, when you compare, it's proper. Okay. So 70 will get inserted here. So this is the final answer where 70 has got inserted. Now you check this tree. Both the properties are satisfied. First property is the structure property. It is a complete binary tree. And second property is heap order property, where every value of the parent is greater than the value of its children. So you compare now, 80 is greater than this children value, 70 greater than is both the children, 45 greater than both the children, 24 is greater than both its children, and 59 is greater than both its children. So this throughout the tree it is satisfied. So now we have done this. So this is a heap, a proper heap, a max heap. So you can just read here what I just explained is mentioned here in the para here. You can just read this entire thing. And if you have not understood anything, then you can let me know. I'll explain it again. Just giving you 30 seconds just to look at this slide and understand. If any doubts, you can let me know. Please understand this step properly, because tomorrow when we are doing heap sort, I won't explain it again. So you will have to remember this. When the heap order property is violated, what you need to do? This is what you need to do, what is being shown in this slide. The heap order is violated here. Okay, heap order property is violated here. So then what we have done is, in all these steps I have shown you what we need to do. So you need to keep exchanging the value of 70 till the heap order property is satisfied. So I'll just come to your chat and check anyone is having a problem. So if new element is greater than root node, then what would be the output? Yeah, you keep on exchanging till you get the new value as the. So suppose you were inserting, just for example, let's call this new value we were inserting was, say, it was 70, say we were inserting 90. Okay. So this entire thing you would have done the same thing. This would have become 90. This would have become 90 till here. Okay. Now what would have done? You would have compared this with this. 90 with 80. What you would have done? You can write in the chat, everyone. Suppose we were inserting 90 here. So the steps would remain the same. But when you reach here, is the property satisfied? Is this heap order property satisfied? You have to keep on exchanging till the heap order property is satisfied. So in this step here, you would have exchanged. So 80 would have come down and 90 would have gone on top. So like we had discussed, in a max heap, the largest value, that is 90, would be present at the root. Okay. Yes, you would swap 80 and 90. Correct. Okay, so it's the same procedure. Any value comes, if it violates the heap order, you have to do. Now this is a max heap. If it is a mean heap, then you have to check whether the new value, this new value is less than the the parent value is less than the new value, if it is a mean heap. But here we are checking for max heap, because I told you throughout the textbook now only max heaps are going to be used. So we are going to only solve with respect to max heap. So there are some more examples. If we get time, I will show you that. Okay. Now we'll just do one. We'll do this and see. So you can note down in your books. Insert the following elements in a heap and note down these elements. 25, 35, 18, 9, 46, 70, 48. And we'll see step by step how this heap is to be constructed, maintaining both the properties. So let's start. So in the first step, whatever is the first value, 25, will become your root node. Okay. So first step is insert 25. So this will become the root node. Second step, 35. Okay. Can you try on your books? What would you think? Where should 35 get inserted? As the left child of 25 or right child of 25? Remember, you have to satisfy these two properties. Okay. To satisfy the two properties, and those two properties are complete binary tree, or the first property is the structure property, which is it should remain a complete binary tree, and second property is heap property, heap order property. So both these properties should be satisfied as you are doing the insertion. So if this first property is to be satisfied, where will this 35 be inserted? As a left child or a right child? Can you type in the chat? Correct. It will be inserted as the left child. Correct. 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 Insert. Do it on your books. Do it on your books. So after inserting, if the first property is satisfied, check for the second property. Is the second property satisfied? If second property is also satisfied, then you're done with that step. If not, you need to exchange the two values, like I told you in the previous example. So coming over here, okay, you will insert 35 like this. Okay, you will insert 35 the left child, and the first property is satisfied. Okay, here the first property is satisfied. It is a complete binary tree, so you're happy with it. So you go for the second property. So second property is value of the parent, value of this parent should be greater than the value of its child. So 25 is not greater than 35. It's violated. This property is violated. So make it proper like this. When you make it proper, what you're doing? You swap the values of 25 and 35. So after swapping, you will get here 35 as the root and 25 as the left child. Okay. So after swapping, you will get like this. So now you check both the properties. First property is satisfied. It is a complete binary tree. And second property also satisfied. That is your heap order. Now when we are checking for heap order, remember we are checking for max heap. So we are checking for heap order, meaning we are checking whether it's a max heap. And the first property we are checking whether it's a complete binary tree. Is it clear? If you have understood this, then you continue, go for the third one, insert 18 and keep inserting like this if you have understood. One by one you insert. After inserting each element, both the properties should be satisfied. Then only go for the new element. So if you insert 18, 18 will be inserted as a right child of this. So first property is satisfied. Is second property satisfied? Is it a max heap? Yes, it is a max heap. So no need to change anything. This is your insert 18. Go to the next step, insert 9. Where will 9 be inserted? So that the first property is satisfied. So 9 will be inserted left of 25. Yes, correct. Correct. 9 will be inserted to the left of 25. Correct. Do it. Insert 9 there. So that first property is satisfied. Then check for second property. Is second property is also satisfied or there is a problem? So when you insert this, 9 will be inserted left of 25. Okay. And first property is satisfied. Check for second property. After inserting, is it less than the parent? Yes, it is less than the parent. So max heap property is satisfied. Okay. Here, this remaining 3 nodes you had already checked in the previous step. So you need not check here again. It will be satisfied. Okay. So only check when you for the new node. If there is a problem, then that problem will occur throughout. Then means throughout that node till it finds its correct property of heap order. So now next insert 46. Where will 46 be inserted? Where will 46 be inserted? Right of 25. Correct. Right of 25. Insert. Insert 46. So when you insert, then you check for both the properties. So after inserting 46, check for the first property. That is your complete binary tree or your structure property. So this is a complete binary tree. So it is satisfied. How you know it is a complete binary tree? Just number it. So when you number 1, 2, 3, 4, 5. If you are getting the numbering continuous, that means it's a complete binary tree. Okay. Numbering has to be continuous. If by mistake you have not inserted 46 here and you have inserted 46 here, you have inserted 46 here, the numbering will be wrong. You will get here number as 6. You will get numbering as 1, 2, 3, 4, 6. That means this is not a complete binary tree. You have not done proper insertion. Okay. I think that you understand by now. So this is the way you have to check whether first property is satisfied. The first property is satisfied. Is the second property satisfied? Is it a max heap? If it is not a max heap, then make it a max heap. We have already seen how it is to be made a max heap. So since first property is satisfied, you compare this value with this. Is 46 less than its parent? If not, second property is violated. So make the corrections. So after doing the correction, if there is a correction, where will 46 end up? You can type in the chat. Where does 46 end up if you have done the correction and you have done it correctly? Yes, you will swap twice and 46 will end as the root. Correct. 46 will end as the root. So you can check here. This is the way you are getting it. Okay. You swap 46 to 25. So 25 comes down. 46 goes on top. Then check 46 with its new parent. 46 and 35 again violation. So exchange. 35 comes down here. 46 goes up. Now it's already the root node. You cannot do any more swapping. So insert 46 there. When you insert, this is the answer you will get. So you need to show all these sub steps. Okay, when you're showing this, when you're showing insert 46, you will have to show all these 4 trees. So the first diagram will be this. You will have to mention here in your answer, in your notebooks or in your exams, that heap order property violated. You will have to write here in the side or at the bottom here. Heap order property violated. So therefore, restore max heap property. And then you have to show these 3 diagrams where you are restoring the max heap property. property. Okay, please note it down that you have to show it like that. To write the reasons always. Do not leave any chance for the examiner to cut your marks. Okay, so continue like that. Insert 70. So when you insert 70, 70 gets inserted here. First property is satisfied, but second is violated. The second violation is corrected like this. You have to again write down here. So first property is satisfied, structure is maintained, but heap order violated. So then these are the steps. First step, we are exchanging 70 with 18. Then you exchange 70 with 46, and 70 becomes the new root node. And similarly, you will insert 48. So again, the steps are shown, wherein there is a violation here between 46 and 48. Therefore, you exchange 46 and 48. Only these two values are exchanged, because then 48 is less than 70. So no exchange happens. So you exchange only 46 and 48. And this is your final answer for inserting the elements in your heap. So this is your final answer where you have built a heap. So this is the heap for these elements. So any questions about how to insert elements in a heap? Is it okay? Everyone has understood the two properties? Okay, please remember, heap is not a binary search tree. Okay, so in a binary search tree, left value is less than the value of the root and right value is greater than value of root. But this is not a binary search tree. It is just a binary tree. Is it okay? I think everyone has got it. So let's go to the next part of this. That is how to delete. Now suppose you have built a heap, but you want to delete the values. Okay. So it's very simple. Whenever you're going to delete, you're going to always delete the value of the root. So like we have discussed, in a max heap, the maximum value or the largest value will be always present at the root. So always when you're going to delete, you're going to delete the value of the root. Okay. So when you are deleting, suppose your original size of the heap is 13. Okay. When you delete this value, the maximum value, you take your leaf node, that is your last leaf node. The last leaf node is present at this value, that is 13, because that is your size of the heap. So you take this last leaf node and you copy this value here in the place of the root node. So you are deleting this. So you delete it, remove 90, but copy the last value to in place of the root node. So when you do that, it will look like this. So copy this value, meaning when you copy this 37, you do not again write it down here. You copy and write 37 here. Replace the root node with this last value. Okay. Why we do that? So that we maintain your first property. Your first property is it should remain a complete binary tree. So when you do the numbering, you see that the numbering remains continuous. Okay. We get from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So your first property is satisfied when we do like that. But is your second property satisfied? Your heap order property. Is it still a max heap? Is it still a max heap? Is this property satisfied? And the obvious answer is no. This property is not satisfied because 37 is less than its children. Okay. So then we have to do the We have to restore these values. We have to restore this property. Okay. So please understand, I'm just repeating this again. It's pretty simple what you have to do. So when you are deleting, whether it's a max heap or a min heap, you always delete the root value. So when you delete this, you copy the value of the last leaf node there in its place. When you copy, it will look something like this. Since you have deleted one value, now the present value of your heap will be 12. Okay, and your first property is satisfied. Your number, and you come to know that your first property is satisfied, but your second property will be violated. Most of the times, no, always it will be violated. Okay, so then you have to get it corrected. So that we will see in the next slide. So how we get it corrected? So we take this and we get it corrected. So we check, compare 37 with its children 70 and 80. Okay, now 37 is less than both its children. What we do? We take the maximum value among 70 and 80. Okay, since 70 and 80 are both greater than 37, 80 is the larger of the two. Larger of which two? We are comparing these two, 70 and 80. So 80 is larger than 70. So we take 80 and we swap these two values. Please note what I am telling. 37 is less than these two values. Okay. So now the question arises, should 70 come up or 80 come up? So that is decided by comparing these both larger values. So when we compare 70 with 80, 80 is larger. So therefore I swap 80 and 37. So when I swap, I get like this. 80 is gone on top, 37 is down. Again check 37 with its children. 37 with its children. Is this greater than this both values? So when you compare 37 with its children, you find that 45 is greater than 37. So you swap these two values. Okay. Obviously you won't swap this with 12 because 37 is greater than 12. And it makes no sense in bringing smaller value on top. So you're going to bring larger value on top because this is a max heap. What we are doing is the max heap. So you will swap these two values. When you swap, 45 goes on top, 37 here. Now you compare these two values. When you compare, you see that this value of the parent is greater than the value of the child. So proper place is found for 37. This is the final answer for the deletion of 90. We were deleting 90. So after deleting 90, we had found that this heap order property is violated here. So we need to restore the heap order property. So you can call this procedure as restore down. You can just do this and you have to write the explanation like this. So when you restore the property, finally 37 will be here at this place. Is it okay? Is it clear, everyone, students, how to do the deletion? So just for you to understand, this is what we were doing, deleting. So whenever you are deleting from the root. After deleting, I've told you what happens. Copy the value of the leaf to the root. When you copy, that means why we are doing that? So that your property, first property is maintained. But second property will always get violated. And then second property has to be corrected, has to be restored like this. So before we stop for this lecture, I just want to tell you, please go through both these operations of insertion and deletion tonight before you come for my next lecture. Okay, you need to understand how this is both being done. The insertion part also, we have shown you one entire example how you are building up a heap. So you need to understand, go through it. Okay, understand why you are doing this swapping, why you are doing the inserting. Go through this delete part. Understand why what you're doing when you're deleting. Why this last leaf value comes back on top. When it comes on top, what happens? What gets violated? And if it gets violated, what you need to do? Okay. So tomorrow I'll be directly referring to both the steps. I won't get time to go into detail and show you all this thing. So please practice it at least once or twice on your before you come for the next lecture. Okay. So before we stop, I'll just take attendance. Okay, there are just less number of students who keep attending this